Our next speaker is Abbas ATAYA, and he is the director and leader of machine learning and software at TDK InvenSense, and he's responsible for building features and solutions for the company's sensor portfolio. So without further ado, I'll hand it over to Abbas.
So yeah, thanks for, first let me thank the community for this great event. It's my first time I contribute to this event, so it's a great opportunity for me. I met lots of people. It's really amazing. Let me start my presentation and start first introducing my company. TDK InvenSense is a provider of MEMS sensor platforms that are found in lots of markets. We are found in the mobile markets, IoT devices. We are as well in the robotics. We are industrial, automotive markets. We're actually a sensor company. We have a large sensor portfolio. We have motion sensors, pressure sensors, microphones, fingerprint sensors, ultrasonic sensors, and gas sensors as well. So really, at the very edge of the system, we're the sensors, that boundary in between the physical and the digital world. But the sensor is always never alone, actually. The sensor is always a part of a bigger system. We have a bigger component that has more resources that's sitting right next to the sensor always. So the way I see sensors is those little tiny nodes that are responsible to trigger a right answer, to provide the right knowledge at the right time, that's going to hand off this information, to a bigger system that's going to take responsibility from there. So when you think about phones, wearables, when you think about smartwatches, we all think about how many times you want to recharge the battery of this device, right? If you buy a smartphone and every 4 hours you're going to recharge it, that's not going to fly. Nobody would want to buy such a device. So that's where the sensors are playing an important role here, being at the sentry and the gateway to provide the right answer at the right time, and being able to take that to the next level. So if I look into this main system, you can see many of those edge sensor devices, they produce lots and lots of data. Instead of forwarding all of this data to a bigger kind of a processor, the main processor or the AP, to the fog or to the cloud, the edge computing is about doing as much processing as possible at this level. So this way, we are reducing the traffic, we are improving the latency, and we are saving power. So actually, this idea is not really very new. This idea is, we can find it in specific purpose hardware where we have FFT engines. Those are there because you want to reduce latency, you want to offload the burden from the main CPU, and you want as well to have a gain in power. So that idea is not really new. And when I talk about doing some local processing or edge computing at the sensor level, it doesn't mean I'm stuck at this level. It only means that I'm going to do as much processing as I can. I'm going to get as many answers as I can at this level, and I only move up in that processing chain when it's needed. So when we apply tinyML on our tiny sensors, our mission is very clear. Our mission is to be always on, is to operate at an extremely ultra power that's in the microamps area. Our mission is to identify a pattern, have the right answer at the appropriate time, and trigger with fidelity that next level of processing. That next level of processing can be on the sensor node itself, it can be on the sensor hub, it can be on a main MCU, it can be on the fog, it can be on the cloud. It's very important to think about the complexity of the problem before trying to solve it. What kind of effort I need to put in, and how often do I need to do that, right? So it's like me asking myself, do I really need to wake up in the middle of the night and go out of the bed? Is that really needed? If I go back to the sensor domain, is a duty cycle possible? What's the impact if I miss some events on the user experience? What is the power cost that I'm going to have to pay if I over-trigger events, if I detect lots of them? Those are questions to be asked. Applying on-chip machine learning for us, it means that We're going to go and try to get that very first trig, that very first wake up, and move up. If I go here, what does that mean? Here at this level, I'm actually not consuming any power. My battery can go for months and for years. It's like I'm just like that, like sleeping, very deep sleeping. So the next level is here, like the user interacts with his device. The user wears his device. So that's the level, very first level of interaction. It's equivalent to me sleeping in the bed and listening. So I listen at this point. Do I need to do that extra step and open my eyes? Do I really need to count my steps? Do I need to wake up my screen? Do I need to voice activity detector to be enabled? Do I need to listen to voice? Do I need to listen to audio? Do I need to go to that extra step and now know what's the context of the user? Do I need to do some activity classification, know what the user is doing? Do I need to detect a gesture? Do I need to enable my wake-up word detector? Do I need to wake up my bigger system and start applying some audio noise canceling, command words detection? Do I need to stabilize my image? Do I need to extract a rough location of myself? As you can see, as I go up in the ladder, my power consumption is increasing. But I only do it when I really need to do it. What's important here to keep in mind is I'm asking myself the right questions at the right times. So that's what's going to help me control. That's what's going to help me stage my computation complexity. That's what's going to help me control my power consumption. And that's what's going to help me reduce my overall power in the system while having a good user experience. As I mentioned previously, our mission is really to do edge computing for the purpose of being always on, consume as low power as possible, all while doing as much processing as we can at this level and trigger the next step of processing when it is really needed. So we embed machine learning on the chip, on this very tiny resource chip with very little memory and very little computation power in a very phased wake-up way. That's what we do. And the reason we do it, our purpose is to optimize for the user experience first and be able as well to save the power of the overall system. I don't want to miss events from user perspective for my products. I don't want to miss events. That's really bad for the user experience. That's why keeping my false rejection rate is really very important at this stage. That's to optimize the user experience, to optimize the performance. But as well, I don't want to detect too many events. I want to keep my false acceptance rate really low at this level because that's what's going to have the most impact on the power of my system. Having more events, waking up the main processor for no reason, that's a killer for the power consumption. So it's like imagining you're having a smartwatch and then the screen wakes up every time, right? You're not looking to the screen, but it's waking up. The battery is going to drain in 1 hour. The user is going to really be pissed off. Or even worse, if you have like an audio system where you have over trigs over the voice detection, voice activity detection, so you're waking up your MCU or even the cloud to be able to do some keyword spotting or speech recognition, and that's for nothing. That's really have a huge cost on the power consumption of the overall system and can impact really badly the user experience. So what do we actually do? How do we apply this in applications? How do we make our sensors smarter? Low-sized sensor, very low power, we are in microamps region. How do we make it smarter? So what we do is actually we rely a lot on the best-in-class machine learning methods out there that's provided by the Tensorflow community and developers. So we have, including dense neural networks, convolutional neural networks, recursive layers, and lots of variety of functions that are out there optimized over the course of the years. What we do is we train our models, that's offline training. Oh gosh. We train our models, we quantize our models, so that's in the fixed point, we create C integer code out of those models using a unified APIs that we have predefined ourselves. And from there, it's an easy path to go and build those models and integrate on any platform. Well, we have some specifications to our own platforms, but it's an easy path to integrate on any platform that you can think of. And this part of conversion between the trained model and the embedded C code, that's a very important part of the chain. That's really going to impact the performance on the edge device it's going to impact the memory requirements, it's going to impact the computation requirements. That's a really important part or piece of the chain for us. That's where we have put lots of focus and work and effort to be able to create our own quantization techniques, to be able to respond to our objectives and be able to take our constraints into account. This is only an example of a TensorFlow model that we have quantized into C code that's fixed point, that's operation optimized. It's an 8-bit quantization at this level. And we have run some evaluation on some daily life user activities. We have 6 activities in daily life advanced recognition, activity recognition, and we have compared the memory footprint of both our method of quantization and TF-Lite micro. So we see here that we have removed all the burden and all the overheads and get a significant improvement in terms of memory footprint. That's about 24x, bringing down from 320 kilobytes to 13 kilobytes the model that's going to fit on a small processor that's sitting right next to our sensor chip. So what's our application and data flow to make it easy for the user? Actually, like the user who's not knowledgeable in this domain is not going to be able to build those models. Our path was to really automate and automate all the pipeline going from data to creating models to deploying models on the sensor chip. Okay? We believe that really that path of manipulating data, playing with the data, annotating data, doing augmentation techniques, building the model and deploying on the final end platform, that's really a complex job for somebody who's not knowledgeable of all those different pieces. So what's going to be important is really how easy it's going to be made for the final user to be able to go play with his data, annotate his data, clean up his data, apply some data augmentation techniques, because data is very important for our models. Be able to process that data, create his own configuration of a model, build that model, quantize that model, and now he's ready to be able to compile that model and put it on the end platform. So for this, to be able to enable the user doing all of this, we have a set of tools that we have created, and the objective out of those tools is that the user is going to be able to inject any type of data that he has for any sensor. There's a template. Be able to annotate that data, be able to clean it up, be able to data augment his database, and then go and configure his model, try to put in some visualization to understand his data for some intuition, configure his models, train his model, evaluate and export to fixed point that eventually is going to run on the final platform. And for sure, that's not going to get along without having a tool that's going to enable the user to live test his final model and try to understand what kind of KPIs he's having out of it. That's the machine learning decision. That's as well the memory footprint that's going to be required, and as well the computation or the MIPS that are consumed by this model. I'm going to show some examples that's following that path. First example is a bring to C model. Well, that's bring to C model. So bring to C, that's a smartwatch feature. Like take that example of smartwatch embedding a bring to C, and that's actually, some people call it like raise to wake screen. It's really when you do that kind of gesture to wake up the screen, and that's for the reason of looking at the time or interacting with the device. Could be having multiple reasons. So that has the role of being the very first stage of waking up your screen, the main MCU, and thus this wake up has a power cost. So missing an event, this is not very good because the user experience is really bad if you do this and the screen doesn't light up. So we want to lower as much as possible the false reject rate, that's the y-axis on this graph. And as well, if we are detecting too many events, that means that we're waking up the screen where we shouldn't be. That's the x-axis, the false accepts per hour. So that's the x-axis. We can see here that the perfect zone really resides in this area where we have a very low false reject rate and very low false accept rate. The machine learning solution, we compared it to some kind of say state-like machine. That's a handcrafted solution that we have spent lots of time on optimizing. And really, we can see the value of the machine learning solution here coming in, where we can see that the two curves here perform way better than the state-like machine design that we have here. That's the violet point and the red point here. You can see that we have improved by 10 times almost the false accept rate while having the same user experience at the same time. So what's the cost of that? The cost of that is really 2.5 kilobytes on an M0 Plus, and that's taking around 6% of the processor bandwidth only. And that's a processor that's 32 kilobytes with 4 megahertz clock. Another advantage of the machine learning here is that really we don't have to do any feature engineering. We are using raw data as input. And that's where we are using some recursive networks there to be able to build our models. Another advantage is the improved latency that we have seen for this gesture. Like the reaction time is really quite, you want it to be quite fast. So 100 milliseconds play a big role in this case. So here, just to focus on the wake up and the power impact of waking up the screen when we shouldn't wake up the screen. So here we have machine learning has provided a 10x advantage with respect to a state-like design machine. So 10x, that's about extending the battery life of about 10 hours. Imagine this on billions of devices. That's going to be megawatts of savings per day. That's what tinyML is giving to the planet. It's power saving. Another example is robotics example. So robotics wake-up word and command words. That's a sequential and staged kind of detection. Here the use case is a service robot. That's you're in the restaurant, so you order food. You have your food, you interact through audio with the service robot. Just, you want to take out the food, you want to bring the food. So that's the use case that we're addressing here. So the wake-up word can be put under keyword spotting model. That's a tiny model. It's not simple, it's just tiny model that's dedicated for that specific wake-up word. And that's the name of the robot, right? And once that keyword is detected, we're gonna wake up a bigger system that's gonna be running the command words. We have 11 different command words to interact with the robot that are trained on a bigger model, much more complicated model. So it has a computation complexity that's at a different level, so it consumes more power. We have tried two different approaches. We have put the wake-up word on the MCU and the command words on the cloud. That's the first option. And the second option is bringing down all the processing on the MCU. That is, we have a sequential detection of wake-up word and the command words running on the MCU. And the MCU, the cost of that is about 50 kilobytes of memory for the whole system, with a 1 millisecond of execution time running on 300 megahertz clock. One clear advantage that you can see here is about the latency. We have speed up by bringing down to the MCU or the processing chain. We have speed up by 250 times the execution time with respect to, or the response time with respect to what we had in the cloud-based solution. And the second one is about the power. We have an 80 times advantage in power by running everything on the MCU as opposed to communicating with the cloud and receiving back the response from the cloud. The wake-up word we have compared with third-party vendors, outside solutions that are outside, with two different solutions, just like remove the names here. And we can see that for our quantization methods and our approach, for the same false acceptance rate, we were able to improve the accuracy by more than 12% at this stage. Third example, just as an example of the phased wake-ups that I was talking about, we have done in our labs so far, it's like experiences we're doing, is keyword spotting for TWS devices. How we can reduce even further the power for TWS devices. We know that battery for TWS devices are actually at a maximum 100 milliamps hour. It's really not that much. So we have the processing chain that's decomposed into 3 stages. We have keyword spotting, we have voice activity detector, and we have audio activity detector. So AAD is going to be in charge of listening if there's any audio event or sound event that's happening in the room or where the person is. And that's running on the microphone hardware. It's really extremely very low power. If that's validated, we go to the next step where we have a voice activity detector. That's Excel-based. If the user who's wearing the device is actually, he's the one who's speaking, and that's going to be an answer by yes or no. And if yes, we're going to go to the next step. That's about waking up the main MCU, and now we're detecting the keyword that you want to detect that's in question. So put it this way, if we're just running KWS alone, the battery is going to last only 6 hours. By adding this previous filter or previous step of a voice activity detector, we're increasing that by almost 1.9 hours. And by adding a second step before that, even a filter of the audio that's running in extremely low power, we're increasing and extending the battery life by about 1.6 hours. So that's where the sensors are. That's where tinyML is providing value, is really optimizing that user experience by lowering as much as possible the overall power of the whole solution. As a conclusion, sensors are really at the edge of the real world. Very tiny resources, very tiny, small-sized, very tiny. But those sensors are never alone. They are always part of a bigger component with the bigger resources. So the role of the sensors here is actually to collect data for sure, because you want to observe the phenomenon, but as well to do as much processing as it's possible, such that it creates that balance in between the false rejection and the false accept. Machine learning, tiny machine learning, put in that purpose, is going to help us find that balance in between the false acceptance rate and the false rejection rate that's going to improve and optimize the user experience, and it's going to optimize as well the power consumption of the whole system. Now, some crucial steps that we still have today is, although we've done lots of progress in the quantization techniques, we want to push that step further, because we believe that step is really going to be of a huge impact on accuracy for sure, but as well on the memory requirements and the computation requirements. So if you want to go really tiny later on, we need to look into quantizations that at the different level of 4 bits quantization, 2 bits quantization, something that we believe is really interesting in looking for later. And as well, being able to efficiently create that C code that's going to be able to leverage some hardware acceleration on the sensor chip. That's something as well that's going to be of a very, very big interest in the future for us. So that's the end of my talk. I'm happy to receive any questions if you have.
I had just one. What do you offer in the way of like an SDK or development platforms for people who want to use your sensors with your software?
Yeah, we have our own, we use our own smart motion board that's for development. We have our own as well proprietary processor, that's the DMP, digital motion processor. And we have as well processors that are combined along with the subsystem MCU, that's an M0 Plus, that's the one that I have shown. So yeah, we have multiple development platforms that we use for our development. That's, if that answers your question.
Okay.
So actually, yeah, one thing as well, in CES we introduced the RoboKit platform. That's like a robot, kind of open source. It has, it's based on ROS. It has many sensors inside from InvenSense and TDK as well. And that one had like a bigger processor that's about an M7 that's running on 300 megahertz. It's where we have benchmarked some of the audio solutions that we have.
Okay.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. Gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texil, and Google. So we are very thankful for their support and, more importantly, for them being part of this community and driving it forward.